As we move into part 2 of section 11.3, we're going to start off with this generic integral. We're looking at 1 over n to the p power. Now, if we're already thinking about integral test, this would lead me to this corresponding integral, and hopefully that integral looks familiar. We spent a little bit of time working on this 7.8 in the end of the part 1 video. We looked at this integral generically, and we looked at all the different possibilities for p. We looked what happens when p equaled 1, when p was greater than 1, and when p was less than 1. That was also where I made a little mistake. I accidentally plugged a in for p instead of in for x. So I actually showed that again at the beginning of 8.1 because we already reached the conclusions that we need here. We don't have to go through and do all the work again. We're just going to use that result. That again, if p was greater than 1, if p was less than 1 or if p was equal to 1, we looked at those as two separate cases, but ultimately we concluded that this diverged. If p equaled 1, we got log of x. If p was less than 1, when you added 1, you got an x in the numerator, and as x went to infinity, the whole thing went to infinity. But then we had if p was greater than 1, so like if p was 2, 3, etc., after you took your antiderivative, the x was still in the denominator, so when you plugged in infinity, you ended up getting 0, and you ended up getting that the whole integral converged. That's saying it a little short. Again, you could always go back and rewatch that if you want, but here's the point, everybody. This is what we call a p-series, and we've already got the results. So p-series are like geometric series. We may not always see them in this perfect of a form. Well, in a couple of minutes, just show a few problems looking at terms of the series. But through a little bit of work, a little bit of pattern finding, we can find out what p is and then make conclusions very quickly. So this is very helpful. And again, this all comes as a result of the integral test. So I generically asked converge, diverge for this, and we didn't really set this up as a problem. We already made our conclusions. So again, p-series diverge if p is less than or equal to 1, converge if p is greater than 1. Here's one issue, everybody. It's kind of the opposite with R. Some people, you have R, and you have to remember what converges, diverges, and for R, well, R was also about absolute value. There is no absolute value here. So again, a couple of things to consider here. So let's think about that, and let's set up a bunch of problems. Again, just converge, diverge. Let's start off with number 1, and let's start off a little simple. Let's start off with 1 over n to the 2.3 power. There's nothing to this one. This is a perfect copy of this formula. Everything is in its perfect place. P equals 2.3, which is greater than 1, converges. Nothing more to be done. That's it. And just like geometric series, once you use R and discuss what it's greater than, less than, once you get that established, you can just conclude converges, diverges. You don't have to write or say anything else. Same thing here. P always goes with the idea of p-series. So just by using this notation, you're already making it clear to your reader you're thinking about p-series, so you could just make your conclusion and be done. That's it. Number 2. N to the negative 2 power. Well, first thing some people do, people say to themselves, oh, well, p is negative 2, but that's missing a very important piece, everybody. A p-series is specifically 1 over n to the p power. So you have to have that n in the denominator. So p does not equal negative 2 here. All we need to do in this problem is just realize, hey, if I just take that negative exponent, stick it in the denominator, now I have a proper p-series, and now p equals 2, which is greater than 1, and once again, this converges. Okay? Number 3, let's just quickly do a similar one. If now you started with plain n squared, we can take that exact same approach. But now, again, we're not doing absolute value. So now p would equal -2, and that is less than 1. So that would diverge. I also want to note here, these other ones, if you thought about the test for divergence, both of these, their limit would go to 0, just the limit of the underlying sequence. But that's not enough to conclude that they converge. Here, the opposite would happen. If you took the limit of the underlying sequence, this would equal infinity, which does not equal 0. We would reach the same conclusion. It's the same series, but now we just did it with a different reason, a different test. This diverged because it's a divergent p series. This diverged because we used the test for divergence. Just to point out, just kind of like what we saw with integrals, there are a lot of problems that are really trying to get you to use one particular technique or one particular test, but it's not always just going to be limited to one. 2 different ways to look at this, but we're getting the same conclusion. And it's not just the same conclusion because we got lucky. We're making the right conclusion based off of the evidence that we are presenting. Okay, I hope so far those aren't so bad, but now let's keep going a little bit, and let's just make them a little bit harder. Number 4, let's look at 1 plus 1 over 8 plus 1 over 64 plus 1 over 125 plus ... Now we're just given a bunch of terms. So just like we saw in 11.2, well, there's got to be something to finding the pattern. Maybe it's getting the full general formula. Maybe it's just finding a pattern. But we got to be thinking, well, what's the connection here? What's going on in each of these pieces? We've got 4 terms here. So hopefully there's some way we can see. Oh, I'm sorry, I missed one here. I need this as 1 over 27. I'm so sorry about that. Plus 1 over 64, and then plus 1 over 125, plus ... Very sorry about that. I miscopied. So now we're looking for patterns. Now hopefully that makes it a lot easier. Well, we're looking what's happening. Well, we always have a 1 in the numerator, but the denominator. Well, this doesn't have a denominator, so let's think about the other terms. When we get 2, we get 8. When we have 3, we have 27. When we have 4, we have 64. 5, we get 125. Each time, look at what's happening here. 8 is 2 cubed. 27 is 3 cubed. 64 is 4 cubed. 125 is 5 cubed. We just found the general term formula would be 1 over n cubed. And as soon as we do that, we're right back where we were up here. In this one, or looking at this, we've got the perfect formula, the perfect form for a p-series. P is 3, which is greater than 1, so therefore this converges. Quickly should point out, we've already talked about the harmonic series in part 1. The harmonic series can be thought of as a p-series with p equal to 1. We already know the harmonic series diverges, but we could also look at that as a p-series and also reach that same conclusion. Okay, let's do another tricky one. Not so tricky. Let's just take a look at 2 more like this. And then we've just got a little bit left to talk about that. Now that we're not asking converge, if it converges to what, how would people really finish this? What is the end to knowing how these series converge? Or I'm sorry, we're figuring out if they converge, but what they would converge to. So we'll get to that in just a moment. But looking at this one, well, again, just another quick rewrite. That looking at the square root of n, well, just like when we do derivatives and antiderivatives, thinking of that as an exponent, and that's all we need. That solves this problem. Now p equals 1/2, which is less than 1. we're getting another diverges. But I really want to point this out because it's a very common mistake. We keep saying how the test for divergence only works if that limit doesn't go to 0. But if the limit does go to 0, like it did in both of these, that doesn't automatically allow you to conclude converges. Again, you have no idea. That's not the way that test works. You could only conclude diverge. And here is another example that if you tried the test for divergence, you get 0. So if it doesn't equal 0, you can conclude diverges. If it does equal 0, this would be inconclusive. So you just have to start all over. And then here, well, what else can we do? Well, you've already saw it. We could treat this as a p-series. Okay, so one more like this, and then we'll talk about our summation part. Number 6. Oh, I should have also very quickly just go back to number 4 right here. We found the pattern here. We said initially, well, 1 doesn't really fit the pattern because it doesn't have a denominator. But if we go back, we can treat it as 1 over 1, and 1 is 1 cubed. So yep, that pattern, even though we were seeing the pattern a little later on, it still does hold for the first term. So now problem number 6, still converge, diverge. For problem number 6, again, we're going to look at a bunch of terms. 1 plus radical 2 over 2 plus radical 3 over 3 plus 1/4 plus radical 5 over 5 plus dot, dot, dot. What do we think about this one? One more time, finding patterns. N equals 1, N equals 2, 3, 4, 5. Hopefully, we're kind of seeing some patterns in some of these terms. When N equals 2, when N equals 3, when N equals 5, hopefully we're seeing something stand out on these. But now, sorry, that's a 4, not a 5. On the 4th term and the 1st term, they seem just a little bit strange. I'm sorry, I miscopied again. This should be 1/2. For the 4th term, that should be a 1/2. But trying to use the ones where we think we see a pattern. When n is 2, radical 2 over 2. When n is 3, radical 3 over 3. The n value, we're taking the square root of it in the numerator, and then we have that exact value in the denominator. This looks like this, but is it perfect? We'll go back to n equals 1. The square root of 1 is 1, and 1 over 1 is 1. How about when n is 4? The square root of 4 is 2, and 2 over 4 could be reduced to 1/2. So this is where we were saying, when we are writing out the terms, it's not always in our best interest to simplify, because that sometimes loses the pattern. But if we're trying to find the pattern, we should be able to verify that that was just a simplification. But now we're in a good position, and now, even though this is not a friendly exponent, we can still deal with it as exponents. 1/2 minus 1, this would be n to the minus 1/2. So I could put it in the denominator as n to the positive 1/2. And we actually looked at this one already. This was really, it looked a little different the way we started, but this is really the same as number 5. P is 1/2 less than 1, so this diverges. Okay. So now we'll wrap up this section. And I'll be honest, as we go through this in an online format, I'm really going to continue to hammer down the ideas of convergence, divergence. That is without a doubt our number one priority as we're moving through these sections. If we were in person, I'd probably focus a little bit more on this next topic, but it's already tough enough getting used to convergence, divergence. So I want you to hear about what we call the remainder, and we'll discuss this a little bit here and there over the next few sections, but all this would be a bonus or two, nothing more than that. So this is really for your information to get a little bit more understanding. Because now that we've done these problems, again, just go back for one quick one and think about problem number 2. That converges, but to what? So if I was looking at the series 1 over n squared, we already know it converges, so that this is going to go to some value. This infinite sum, when I start putting in the terms 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25 plus ... that this is, even though we add up for infinity, again, which is always a little strange, adding an infinite number of terms, we are getting some nice value s at the end. Now, when I say nice value, that doesn't mean it has to be a nice whole number. Maybe it adds to 14.3, or maybe it adds to the square root of 3, or maybe it adds to pi over 6. Any of those things are possible, but it's just that we're getting some nice answer. We're not getting a does not exist. We're not getting an infinity or negative infinity. But what is that sum? Well, as long as we know it converges, this is where computer software could kick in. That we could actually just start adding. We could use a program like Maple. Maple won't let you input infinity here, but you could easily go from n equals 1 to 10, and then let n equal 1 to 100, n equals 1 to 1,000. And we could just look a little bit and get a sense of like, okay, when we only added the first 10, we got 6. But when we added the first 100, we got 10. Well, we got to keep going. But if we add the first 10 and we get 6, and we add the first 100 and we get 6.3, and then we add the first 1,000 and we get 6.32, we should have a feeling we're getting close. How close, we're not sure, but we should at least have a good feeling we're getting close. That's where the remainder comes in. The remainder, by definition, r sub n, is the remainder after adding n terms. And r sub n is always going to be what is the final sum minus the partial sum after adding n terms. So again, a quick for instance, if I knew s went to 10, and if I added the first 100 terms and had 9.7, my remainder, it's kind of like my error, my remainder would be 0.3. I'm 0.3 of a unit away from that final sum. So if we know how to figure out our remainder, we can start figuring out, like if we are an engineer and we need to be accurate to the nearest 100th, well, we need to keep going. My remainder is not close enough. If I want to be within 100th of this, I need to have something like 9.99 or better. So that remainder is not enough, keep going. And the integral test really helps a lot with the remainder. This comes up at the end of this section. It's on page 763. The book notes this, that the remainder would always be bounded by these two improper integrals. The integral from n plus 1 to infinity of that corresponding function, and the integral from n to infinity of that corresponding function. Now we could talk about why this makes sense. It has a lot to do with just, again, going that extra term. If you start, thinking about if n is 10 and now n is 11, you've gone one extra space further away. So it definitely makes sense. This area under the curve would be smaller than this. You're covering a smaller base. Going from, again, 10 to infinity here and 11 to infinity, the bigger base would give you a bigger area. But we could go back to that initial picture and talk about why the remainder falls in between here. But I just want to make that point. And this is where I was saying in class, we'd probably do a little bit with this. Solve these generically to say things like, well, if I want the remainder to be 0.1, let's solve this and figure out, well, let's solve this integral a little generically while n would be plugged in. And after we solve this integral, we'd still have an expression with n, and we could figure out that, hey, if I want the remainder to be less than 1 over 100, n has to be bigger than 15. So that's how we would do it. That would be a good way to get us started with remainders and errors. There would be other ways that get developed as well, but that's a very good starting place. And again, this is where computer technology really helps so tremendously, that as long as we know how far to tell the computer to add, it's no big deal to tell a computer, say, add the first 100 terms versus add the first 1,000. If we're doing that by hand, that's a tremendous amount of work, but for a computer, that's no problem at all. So like I said, we'll talk a little bit more about remainder, but really the next section, we're back to these tests. We're going to talk about the comparison tests. We're going to have 2 comparison tests. We're going to be looking at series that are almost like a series we already know and find clever ways to compare them. So you're going to already have to be familiar with some series, and those series are geometric series and p-series. We're going to lean very heavily on those 2 as comparisons. They're very quick series to conclude whether they converge, diverge, so then we could do some comparisons to say if these other series that are close to them also converge and diverge.